Friday. We also did 1.3. 1.3 was our transformation.
If I find it, I do. Okay, I need help on number 5.
Okay. I'll borrow this. So number 5. Now we're given a graph, and they kind of gave us 2 points, and they did give us 2 arrows. And they told us this point here is 4, 300. And then they gave us this is 100, this is 2. So if we wanted to use rise over run, the rise is positive 100, the run is 2. So we can use rise over run. 100 divided by 2 is 50. So the slope is 50. Now, we'll interpret the slope first, then we'll find the equation. Now, I believe the x-axis is time in months. Is that it? So we could say for every month, the balance.
This is time, weeks, and then balance dollars.
Okay. Weeks. So for every week, because we wouldn't need the S, the balance increases by $50. Because when we interpret the slope, we're just trying to say, what does the slope tell us? What is the slope telling us about this graph in terms of the problem? So x and y-axis. Now, Brooklyn, I think you were asking this the other day. X and y on top. I finally understood what you meant. In terms of slope, y is always on top. Y is always on top in terms of slope. When I answered your question the first time, I was thinking of it more in terms of just fractions, not in this context. But in this context, y is always on top. If there's not a denominator, that value is y, and our x value is understood to be 1. Now we use point slope to go from this here. So they gave us a point for 300. So 300 would be y. 50 would be our m, and x would be 4. Now we can distribute the 50, so we'd have y minus 300 is equal to 50x minus 200. At this point here, we would add 300 to both sides. Minus y is equal to 50x plus 100. So the two answers, parts of the answers, one, for every week the balance increases by 50. That's interpreting the slope. The equation we want for our answer is y is equal to 50x plus 100. So we need both of those. For 3 through 8, there's 2 answers. We need both. Questions on any of this here? Now, if you don't put it exactly like that, that's fine, especially for every week, interpreting the slope. As long as it is saying what the slope is saying, that's all that matters. Does that make sense? Because we could have said not for every week, but for every 2 weeks, the balance increases by $100. Saying the same thing, just in different words, in a different phrase. Does that make sense? Yeah. Or we could have said the balance increases by $50 every week. Same thing. Different wording. As long as it is saying the correct thing, I will take it. Any other questions on this here? Are you ready for the notes?
Yeah.
Well, For those of you who are in the ACT prep class, we're doing more systems. But what we're doing here is not systems of equations with 2 variables. We're doing systems of equations with 3 variables. We did not do these, I don't believe, in Algebra 1. We mainly focused on 2 variables in Algebra 1. But here we're looking at systems of equations with 3 variables. Now the variables we have are x, y, and z. And is an equation of the form ax plus by plus cz equals d, where a, b, and c are all not 0. Because if all 3 are 0, this entire side of the equation is just 0. So a, b, and c, the numbers in front of x, y, or z, we have to have at least x, y, or z. We have to have one of them in all 3 equations. Most of the time we'll have 3. This here is an example of a system of linear equations with 3 variables. Most of the time we'll have 3 equations with 3 variables. We could have 1 equation with 2 variables, but we'll have these here. And a solution for a 3-variable system of equation is an order triple of the form x, y, z. X will always be first, y will always be second, z is always third. And that's mainly because we always put them in alphabetical order. So if we're looking for x, y, z, x first, y second, z third. If they gave us the variables a, b, c, a's value would go first, b second, c third. We do it in alphabetical order. Now, there's 3 different types of solutions that we can have. The first is that we have one solution. We have exactly one solution. There's one point where all 3 equations are true, and that's right there. Now, graphically, whenever we graph a 3-variable linear equation, it's going to look like a plane. It's going to look like a flat sheet of paper. And where all 3 of these equations cross is our point or our solution. And this is one of the setups. We can have exactly one solution where all 3 cross, where all 3 equations are true. Or we can have infinitely many. There's going to be a line or plane where it's true. And here, every point on that line is true. There's infinitely many. Now, I am going to point out that we're not saying all real solutions, because for our 2-variable system of equation, we did say all real solutions because they were the same line, so every point on that line is true. And it's not all real solutions, because that point right there does exist. It is a part of all real, but it does not satisfy this because it's not on that line. So there's infinitely many solutions along this line. It's just not everything. It is infinite, but it's not everything. Now, in algebra and trigonometry and pre-calculus, we will get into more than here on actually defining it, because we can actually define this here. Like we could say it's 2a, 3a minus 4, and a is defined by this here. So any value of a that we can plug in there will give us a solution. Yeah. No, I just made this up, but I mean, this could be a solution, because when we talk about finding the infinitely many solutions, or finding some of them, we create this here, and we would go about it using different processes to find it, and that would define the system of equation. But for this here, we're just going to say it's infinitely many. Because we've had one, we have infinitely many, and we can also have no solution, where none of them cross or overlap. Because here, the first one, we do have 3 spots where 2 of the planes intersect, but they don't all 3. They don't all 3. All 3 of them do not intersect at any one of those lines. Because all 3 do not intersect, it's no solution. Or here, we have 2 spots where the planes intersect, but because all 3 do not intersect at those spots, it's no solution.
So it's the left and the parallel.
They're all parallel, so there is no solution. There is no intersection, so there is no solution. Now, mathematically, when we solve this, what we'll see for a no solution is this here, 0 equals 1. We get a false statement. Doesn't necessarily have to be 0 equals 1. Most likely, one of the sides is going to be 0. The other side is going to be some number. It doesn't work. infinitely many is if we get what they call the identity 0 equals 0. So 0 will always equal 0. That is a true statement. We're looking at infinitely many. Now, we do have these 3 steps. There's 3 steps in solving it. I phrase them a little different. But the main thing we're looking at is eliminating variables to get down to the end. Because when we solve a 3-variable system of equation, well, we can't just solve for 3 variables. Those of you who had me for geometry, I did pose this question then. Because at any point up to this point in geometry, algebra 1, have we solved for more than 1 variable at the same time? Well, not really, because we solve for 1 and then we can find the others. Same thing's true here. I can't just solve for x, y, and z all at the same time and find it. We have to find one first to be able to find the others. So the real goal in this here is to take the 3 equations with 3 variables, down to 2 equations with 2 variables, down to 1 equation with 1. Because if we can get it down to 1 equation with 1 variable, I can solve that. And then we will do what I call work backwards. So when we look at this here, the first main step, I would write it off to the side because this is going to take up most to, if not all, the space that you have left on that second page to work this here. So I would write it above the problem in between the steps and that little gap there. Because the first thing I do with this here is I pick a variable to eliminate. And an eliminator equation. Pick a variable to eliminate and an eliminator equation. We'll go more in depth and explain this here in a second. So again, we want to go from 3 equations with 3 variables to 2 equations with 2. And to do that, we need to eliminate one of the variables out. Now, the way I pick it is I look at all 3 variables and see which one is easiest to eliminate. And to do that, I'm going to look at x first. We're going to just go left to right. So I look at this here, and I want to turn one of the variables or numbers into the other 2. So I always look at the smallest one first, 2x. What can we do to 2x? What can we multiply 2x by to get it to be 4x? 2. That's pretty easy. I can multiply it by 2, we get 4x. What can I multiply 2x by to get 6x? 3. That works well, because I can turn 2x into both 4x and 6x easily, so it's a good one to eliminate first. Let's look at y. So we have 2y, 3y, and y. I'm not so focused on the sign, I'm just focused on the number. And the smallest one is 1, yes? So here, if I wanted to eliminate y, what can I multiply 1y by to get 2y? 2. What can I do to 1y to get 3y? So it's easy to multiply that one and get it to be the same as the others. So y is a good choice. This one is, I wouldn't go that far, but it's not as good as the others. Because what would I multiply by 3 to get 4? Well, there's not really a number. To get this one to work, I'd have to multiply the 4z by 3 and the 3z by 4. I'm having to do 2 multiplications. And it's not that that's wrong or incorrect, but if I have 2 others that are nicer, I would go with them first. Does that make sense? Because if we had an equation where all 3 were set up like z, where I couldn't easily multiply 1 to get to the other 2, then I would have to use one of those. I mean, you can go for y, you can go for x, whichever one is easiest. So, at this point, we need to pick an equation, or not an equation yet, but pick a variable we want to eliminate first. So we can eliminate x first. That's the first one we're going to eliminate. Now we need to pick an eliminator equation. And really what that is we're going to pick the second one. And what we're doing, the eliminator equation is being used to eliminate x out of the other 2. We're picking an equation that we're going to use to remove x from the other 2 equations. So what I'm going to do is rewrite the other two equations that are not the eliminator equations back down. So I write this here, I put a line between them just so I can keep the two equations separate and what we're doing separate. Now I'm going to write off to the side, and I would suggest, especially when you're doing these on your own, to have scratch work space on either side, to not write it all going down one column, because we do have multiple steps after this one. Now, any questions on how we've set this up so far, how we picked the variable we're eliminating, or our eliminator equation? We're good with all this so far, yes? Now the first thing we want to do is eliminate x. So the eliminator's equation is 2x. What do I need to multiply that by to get it to be 4x? What do I need to multiply 2x by to be 4x? 2. So what I'm going to do is I'm going to multiply the entire eliminator equation, both sides, by 2. Because I want those x's, the number in front of x, to be the same. We can get the signs to be the same, but specifically I want them to both be 4 in this case. Because when we multiply through by 2, 2 times 2x is 4x. 2 times negative 3y is negative 6y. 2 times 5z is plus 10z. And negative 7 times 2 is negative 14. We're going to multiply it all by 2 and then put it under that equation so that we get 4x minus 6y plus 10z is equal to negative 14. Questions on this here? Now we're either going to add or subtract. And whenever we do this, I highly recommend actually doing the subtraction or addition with the one we're trying to eliminate to make sure we got it right, not just cross it out. 4x minus 4x. 4 minus 4 is 0. That's what we wanted, yes? So we know that we're going to subtract all the way across. I put the subtraction between each of our terms just to remind myself that we are subtracting so that I don't go about halfway through and start adding. Here, we already said 4x minus 4x is indeed 0. Now the next one, 2 minus negative 6. Our negative make a. So 2 plus 6 is 8y.
Oh, wait, never mind. Wait, you don't drop the x, right?
It was 4x minus 2.
4x minus 6y plus 10z.
I thought it was,
Let me see.
mine says 4x plus 2y. So are you negative? Oh, negative here.
Yes.
Oh.
So the x just doesn't drop.
Well, we would have 0x,
Oh, yeah.
and then 0 times x is 0, so it's
Gone.
gone. Any other questions up to this point? No, you're good. It's good to ask before you get lost. The next one, 3z minus 10z is negative 7z. And lastly, 12 minus negative 14. Negative and negative make a.
26.
And again, sometimes, especially with these minus negatives, you can type them in. We can type this into the calculator. 12 minus negative 14. 12 minus negative 14 is 26. If we want to double check it, typing it in is not a bad solution. It does help us. Any questions on this here? Now we have one equation, one of our two equations with two variables, because that's the goal, is to go from 3 equations with 3 variables to 2 equations with 2. Now we're going to repeat the process we just did. So we need to see what do we need to multiply our 2x minus 3y plus 5z equals negative 7 by so that our x's match up. Now we need the x to be what? 6x, yes? So what do we multiply 2x by to get it to be 6x? So we can distribute the 3. 3 times 2x is? 3 times negative 3y is negative 9y. 3 times 5z is 15z. And 3 times negative 7 is negative 21. Now the question is, will we add or subtract? So we can do add first. 6x plus 6x is?
Oh, wait, no, I thought this was.
So, bless you. It will not always be minus. The biggest thing with subtraction, if the signs are the same, so if they're both positive or both negative, then we would subtract. But if the signs are opposite, one is positive, one is negative, then we would add. Now, when we subtract, 6x minus 6x is, now we look at the next one, negative y minus negative 9. Y. Yeah? No, it is 8y. Because our negative would make a plus, so we have negative y plus 9y, which is 8y. 4z minus 15z is negative 11. 4 minus 15, 15 minus 4. And lastly, negative 3 minus negative 21. The negative would make a plus. 21 minus 3 is 18. Now, if some of these double negatives get really tricky or you're having trouble keeping track of them, put them in a calculator. Let the calculator do it for us. You're good? Any questions on how we got to this point? Step 2. There's a pencil on my desk if you need it. Step 2 is similar to step 1. Pick a variable and eliminate it. We're doing it again. But this time we're not going to have an equation to eliminate the variable out with. We have 2 equations. We're going to use those 2 equations to eliminate one out. Yes. At this point, if one of the variable already has the same number in front of it, that's the one we're going to use. Because if we look at the y's, both of them are 8y, yes? I don't have to do a thing to get them to be the same. They are already the same. So we're going to do it. Yes? We will get to one where it's not. Essentially, if it's not, like what we did to get x's to be the same, we'd have to do it. Or if it's not, I'm not able to just do a multiplication with 1 to get them to be the same, then I'll multiply both by a number to get them to be the same. Because our main focus is getting the number in front of one of the variables to be the same so that we can add or subtract the 2 equations from each other to get us down to one equation with one variable. Because we now have 2 equations with 2 variables. And if we do this here, so 8y and 8y have the same sign, so we would subtract. Because 8y minus 8y, 8 minus 8 is 0. So these do cancel out. And if we look at the rest of it, 7z minus negative 11z. So negative 7 plus 11 is 7 minus, or 11 minus 7. Mm-hmm. 26 minus 18. 4z equals 8. Yes? Mm-hmm. Solve. So we would divide by 4. And z is equal to,
Okay, so it's probably a stupid question or whatever. Can you like, are you able to really answer by like, so you were asking that, so like after you do 20 times by 2 and 4 and all that,
yes,
would that be the same?
not really.
Okay.
It could, it's just worked out that one of the ones we multiplied matched, but it's not necessarily the case every time. Solve and solve backward. I haven't really seen solve backward put down anywhere, but this is kind of my terminology, the way I think of it. Solve and solve backwards. Because we did the first half of it, we solved, we found z, yes? Now when I say backwards, we're going back up the page. Because again, we had 3 variables, yes? X, y, and we had to find all 3 values. We found z, yes? If I go back up the page a little bit, here I have 2 equations with 2 variables, yes? And we now know one of the 2 values. So we're going to pick one of these 2, doesn't matter which. Left or right, all's choice. I'm going to take this equation. 8y minus, well, I know 7, we're not going to put z, because we know its value is equal to. Now we're going to solve for the value of y, because that's what I mean by go backwards. We're going back up the page. Yeah. So, right, so we'd have 8y minus 14 is equal to 26. At this point we can, yes, because we do the opposite sign. Since the 14 is negative, we would add. Telling us 8y is then it would be 5. We would divide both sides by 8. You're good. Telling us y is 5. So we now have 2 out of the 3, yes? We're going to keep going back up. Because now we need an equation with all 3 variables, yes? So we have 5 different choices. We have the 3 they gave us to start with, yes? Now the question is, where are the other 2? Well, one of them's right here, and the other's right there. Those 2 technically are one of the 3 equations. It's just a manipulation of equation number 2, yes? I wouldn't pick those 2. I would stick with one of these 3. We can do the top one. Now, I'm going to do something that only I can do with this here. Make it all go away. No, I was just giving myself room to put this here. So I picked the top equation. So 4x plus 2 times 5 plus 3 times 2 is equal to. Now, at this point, there's 2 things we can do. I didn't mention this in the other classes. One of them is I can multiply this out. 5 times 2 is 10. 3 times 2 is 6. Is equal to 12, yes? And then we have 10 plus 6, which is? Could I have typed 2 times 5 plus 3 times 2 in the calculator? Two times 5 plus 3 times 2. Enter. So instead of multiplying and then combining, I could have just let the calculator do it all for me. Either way works. Now what we need to do next is to get x by itself. So we would subtract 16, telling us 4x is equal to -4. Well, it's not like -1. It is -1. So that there, -1, 5, 2, is the solution to this system of equations. And we would write it out like that as that ordered triplet. Yes. So we will be finishing these note sheets tomorrow. But one of the things I do want to point out with this is trying to do this all at once is a lot. Would y'all agree with that? Trying to do this all at once is a lot. But if we think about it in each chunk, doing it one step at a time, that's not a lot to it. And that's the biggest thing with all of Algebra 2, is taking it one step at a time. Because Algebra 2 gets this notion of it being difficult because, one, it's new. Because y'all never solved a 3-variable system of equation before. And most likely by the end of the day Wednesday, or not even the end of this hour Wednesday, you're going to be really questioning why I spent today and tomorrow working with this, but that's fine. I set it up that way on purpose. But also, if you take it step by step, one step at a time, it makes these not as challenging as you think they are. Because that's the biggest thing with Algebra 2, is taking it step by step, not trying to do it all at once, or trying to tackle it all at once. Do it one step at a time. And luckily, especially with the ACT, and we'll cover this tomorrow with our systems of equations, the fact that we have multiple answer choices, I can throw them in. Especially if it gives me 3 values, I can plug it into the first equation. If I get a true statement, I move to the next one. If it gives me a true statement, I can move to the third. If it gives me a true statement, and then I have the solution. Because if one of them doesn't work, it doesn't matter if it works for the other 2, it's got to work for all 3. Or if it's just 2 variables and 2 equations, it's got to work for both.